All right, for this type of problem, we have our reactant molecules and our product molecules. So our reactants are in a line, the products are like this little triangle. So remember, our equilibrium constant is our products over our reactants. And this one's confusing, so sometimes I like to remind myself, what is my product? What is my reactant? Okay, so, and then the equilibrium constant is 9. And remember, if there's a 9, if there's just a 1 number, there's always a 1 on the bottom, just like in math. Okay, so it says the equilibrium constant is 9. Predict the number of R and P molecules in the sample when the interconversion reaction reaches equilibrium. So what's happening is that we have these different molecules, and this product molecule can spontaneously pop back into a reactant molecule. And this reactant molecule can spontaneously pop back into a product molecule. So they're kind of just like interchanging all the time. So we need to know the total number of molecules. So if we look at this picture and we count them up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 total molecules, okay? And sometimes that can help us see what's going on. All right, so these can interconvert. So we need some kind of fraction that adds up to 10. So what I mean by that is that we have 9 products and 1 reactant. If we have 9 plus 1, that will give us our 10 total. So that tells me that for this reaction to reach equilibrium, 9 of these have to be this product molecule, 1 of them has to be this reactant molecule, and then we'll know that it's at equilibrium. So this would be, we need 1 reaction molecule. Also, they don't put it in order, so that's not helpful, so just be careful. So reactants, we need 1 of those. We need 1 reactant with 9 products. This is a total of 10. We can only have 10. Our sample size is fixed to the number of molecules in our box. And so that will be at equilibrium, we should have 9 products and 1 reactant molecule. Okay, let's look at another one of these. These are confusing. So here we have an equilibrium constant of 1. So that's like we have 1 to 1. We have 1 product, remember products go on the top, for 1 reactant. And it might be helpful to, this one's too hard. Products to draw. Well, products look like something like this. Reactants look like a flower, more like a flower. Okay. And let's count them up. We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a total of 12. So the only way that we can get to an equilibrium of 1 with 12 is to have 6 products and 6 reactants. That will simplify to 1 to 1, 1 product for 1 reactant. So when I answer this question, I will have 6 reactants and 6 products. So that one's not too bad. Let's try one more because that one was too easy. Okay, how about this one? This one looks a little bit trickier. So this one, we are looking at our equilibrium constant. It's telling me that I need 3, remember products is on the top, 3 products for 2 reactants. The reactants are like a pyramid and the products are like, I don't know what this is, like a W. Okay, and then our total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think we have 10. Let me count them one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great, we have 10. So we need to figure out, we start with 10 total. Right now, our concentration is, we have 1, 2, 3, 4, 5, 6. We have 6 products. And we have 1, 2, 3, 4 reactants. Oh, well, this one's also easy. So look at this. We have 6 products for 4 reactants. This already is at equilibrium. This would simplify if we divided both of these by 2. This would simplify to 3 over 2. So this one's already at equilibrium. We already have 6 products. And remember, this is backwards, so just be careful. 6 products for 4 reactants. So that one also was pretty easy. So if it's not easy, you might have to shuffle. So you might have to move one of the products to a reactant and see if that works. And then another one of the products to the reactants and then see if you have your fraction. So the key is that these are shuffling. So this one could all of a sudden become a reactant. And maybe that gets you to your fraction. So if you have questions on that one, let me know. Let's see. Okay. All right, we did that one. We're almost there. Okay, let's look at this this question. This question is a little bit confusing too. So let's read through it. So let's start one, and then let's read through it. Ammonia and oxygen react to form nitrogen and water like this. Imagine we have 154 millimoles of nitrogen and 462 millimoles of water, and they're added to an empty flask. What is the rate of the reverse reaction? Okay, so we need to know what's happening at equilibrium. So at equilibrium, the forward rate, so this is at equilibrium, the forward rate equals the reverse rate. So this is for a reversible reaction. So if we have A plus B going to B plus C, or C plus D, the forward rate and the reverse rate is equal if we are at equilibrium. The other thing that's happening at equilibrium is the concentrations are constant. So sometimes it gets confusing because we think that equilibrium means they're equal. No, they're not equal. It just means that they're interconverting at an equal rate, so then their concentrations stay the same. Okay, so then if we disrupt an equilibrium, if we add more A all of a sudden, then that's going to shift the equilibrium away from A. So by disturbing the equilibrium, by adding A, you can push the equilibrium away. So then the forward rate goes faster. If you add more product, then that's going to push the reaction away from the products. That's going to go towards the reactants. So we are imagining we have some concentrations in a flask, or some stuff. Okay, so it says, what is the rate of the reverse reaction before anything has been added? So this is saying it's added to an empty flask. So we are imagining we have some kind of beaker or flask, and we haven't added anything to the reaction. The only time the reaction rate is going to be 0 is if we haven't added anything. So nothing's in there, nothing's happening, 0 reaction. 0 reaction rate. Okay, the second question says, what is the rate of the reverse reaction just after we add N2 and H2O? So we have N2 plus H2O. This we have mostly reactants right at the beginning. So that's going to mean that the forward reaction is going really fast at the beginning. It's going to try to move us towards equilibrium, towards the products, which are N2 and H2O. Or oops, this should be O2, excuse me. So the reverse reaction is going to be small because there's no products right now. So it's going to be greater than 0, but it's going to be less than the rate of the forward reaction right at the beginning. And then it says, what is the rate of the reverse reaction at equilibrium? This is a definition. At equilibrium, the forward rate is equal to the reverse rate. At equilibrium, they're greater than 0 and equal to the rate of the forward reaction. So it's asking about the reverse reaction. So once it's reached equilibrium, the rates are equal. And then at the very end, it says how much N2 is in the flask at equilibrium. Well, we can't say for sure, but we can say if we started with 154 millimoles of N2, that's going to get used up to go to the product. So we're going to have a little bit less. We are going to have some because it's at equilibrium, but it's going to be less than what we started with. So this is just a reasoning question. Oops. Row 2. I don't know if that's true. Just after. Does it want this one? Okay, I don't agree with that one. All right. Let's try another one. Okay, we have a mixture. So now we have the reaction. The reaction is already happening. So if that reaction is already happening, the reaction can't be at 0. It's always going to be either at equilibrium or we're going to be shifting to equilibrium. So imagine that we have this. We need to identify this in our equation. This is a reactant. Okay, so if we add this, it's going to shift the forward reaction faster, and the reverse reaction is going to go slower. So it says, what is the rate of the forward reaction before any HCH3CO2 has been added? So right now, before anything happens, it says it's at equilibrium. So that means that that's the definition. The reverse and forward reaction are equal. The second box says, what is the rate of the forward reaction just after this has been added? So remember, this is a product. It's going to move away from that. So it's going to go, the forward reaction is going to be greater than the reverse reaction. So greater than 0 and greater than the reverse reaction. Because if we put another product in, or excuse me, another reactant in, the equilibrium is going to shift away from that. So this is the forward reaction, is going to shift away from that. We have more reactant to get two products. Okay. What is the rate of the forward reaction when the system has again reached equilibrium? Well, if we're at equilibrium, the reaction rates are greater than 0 and they're equal to each other. So that's our definition of equilibrium. At equilibrium, the reverse and the forward reaction are equal. And then it says how much more HCH3CO2 is in the flask when the system has again reached equilibrium. So we had some in there already, and then we added more, but some of this went to our products. So we don't have all of that. So we're going to say we have how much more? Well, we have some more, but we have less than 119 millimoles. Okay. All right, very good. And I think we have one question. Oops. One question left here. All right, a chemist measures the energy change. So remember, this is our delta H during the reaction. So remember, if we have delta H is positive, that's going to be called endothermic, and it's going to have heat is absorbed. And if we have a delta H that is negative, that's going to be exothermic, and heat is released. Okay, so let's see what else we need to know. Blah, blah, blah. The reaction is, okay, let's go ahead and start one. A chemist measures the heat of reaction during the reaction. So we have a positive value. If it's positive, it's endothermic. And sometimes I get this backwards, so I would write this on my note card to make sure you don't get backwards on the test. Okay, suppose 62.9 grams of mercury oxide react. So it did react, so reacted. Will any heat be released or absorbed? So this is telling me this much is released or absorbed for this reaction. So if I have this much that reacted, then it's an endothermic reaction. So yes, it is absorbed because it's endothermic. I have not seen this question be no, so watch out. Should always double check, but it's always going to be yes. It's either going to be yes or absorbed or yes released. Okay, last question. If you said heat will be released or absorbed in the second part of this question, calculate how much will be released or absorbed. Well, we know that we have 62.2 grams of mercury oxide, which we should not be using in our lab. And we need to figure out how many moles this is. So we need to use what we just learned. We need to convert this to moles of HGO, because this equation is telling me for every 2 moles of HGO, I get 182 kilojoules. So this is kind of like a conversion factor. So I need the molar mass of HGO. So remember so the molar mass, we just need to add Hg and O. So I'm going to do that on my ALEKS calculator. So Hg is over here. I'm going to add O, and that gives us a molar mass of 216.5914. And remember, the units for this is grams per mole. Okay, so this is my molar mass. This is in grams, so this part needs to go on the bottom. I'm going to be dividing by my molar mass, grams for 1 mole, and then I have moles of mercury. So let's do this. I think I can store that. I don't know how to do that, so let's try it. Okay, 62.2, 69.2 divided by, let's try this memory button. There we go. Gives me, equals 0.31949 moles of mercury oxide. Okay, and then we have one more conversion factor. This equation is telling me I have 2 moles of mercury oxide for 182 kilojoules. So we have this is still our given number. Okay, moles of mercury. And I'm trying to figure out kilojoules. So that's going to go on the top. So I have 182 kilojoules, and that's just from this equation. 182 kilojoules for 2 moles of mercury oxide, HGO, right here, 2 moles for this much. Okay, so then I just cancel out moles of mercury. This is mercury oxide. And then I'm going to multiply this number by 182 kilojoules per 2 moles, and that gives me 29.07 kilojoules. And let's see, this gives me this number in 3 sig figs. This one's in 3 sig figs, so my answer must be in 3 sig figs. Also, it gives me a hint on the homework. That's going to go away on the test, so just watch out for that. So 29.1 kilojoules. We'll check that. Okay, let's do one more like that, and that will be our last problem. So we have a negative number. Do you remember what that tells us? I don't know if you remember, but negative is an exothermic reaction. Heat is released. So exothermic, and again, this box is always yes. So it's exothermic energy is released. And then we have to do our conversion. So it says 88.4 grams of C3H8 react. We need to figure out how many moles of C3H8 that is. So I need my molar mass. So, and grams is on the top, so I'm going to put the molar mass on the bottom. So I'm just going to type it in like this. I'm going to put 88.4, and then I'm going to divide, let's see if it'll just divide by my molar mass of 3, let's type it in, 3 times carbon plus 8 times hydrogen, and that gives me how many moles? I have about 2 moles of C3H8, and then I'm going to use this as my starting point. I have 2 moles of C3H8, and I need to know how many kilojoules of energy this releases. So this is telling me for every 1 mole of C3H8, I have negative 2,220 kilojoules per mole. So I'm going to cancel moles, and then I multiply this number by this value, divide by 1, which is, you just don't have to do that, 2220. Okay, and then I have 4 significant digits here. I have 3 here. So we're going to keep 3, and that's what this box tells me too. So that's going to go away. Remember, that's going to go away on the test. Okay, so I just need 3 sig figs. I'm just going to put this in scientific notation and round to 3 sig figs. So also the negative sign is important here. You're going to release energy, so it needs to be negative. 4.45 times 10 to the 3. And then we check. Okay. All right, let me know if you have questions. The notes should be posted on Canvas if you need to look at the notes.